Hello, this is Mrs. Myers. Today we're going to be learning section 5.3, bisectors and triangles. Now in section 5.2, we talked about bisectors, segment bisectors, angle bisectors, and we know that a bisector divides something into two congruent pieces. So a segment bisector would be a segment that cuts another segment into two congruent segments. So if you have a segment bisector, it cuts into two congruent segments. If you have an angle bisector, it cuts into two congruent angles. This one that I've drawn here is a perpendicular bisector. Of course, we could have a segment bisector that is not perpendicular, still could be cutting into two congruent pieces like that. We learned all about that in 5.2. Now we're going to be applying those concepts to triangles. So bisectors in triangles. I'm going to skip this warm-up for the purpose of the video here, but right here there's some important vocabulary words. When three or more lines intersect at one point, they are said to be concurrent. Concurrent, C-O-N-C-U-R-R-E-N-T, concurrent. They come together, three lines in this case come together at point P. They are three concurrent lines. The point at which they intersect is called the point of concurrency. It's the intersection point, but when it's three or more lines coming together, they call it the point of concurrency. It turns out that in a triangle, if we draw the perpendicular bisectors of each side of a triangle, they're going to be concurrent. They're going to all intersect at one point. The bisectors of the three angles, so in other words, the angle bisectors of triangles are also concurrent. They come together and they meet at one point. It's kind of a cool thing, actually. It's kind of wild that that happens every single time. Perpendicular bisectors of a triangle. In this theorem, we have the concurrency. It says that if you draw the perpendicular bisectors of all three sides of a triangle, then they're going to meet together at one point, and that point, this is the theorem part of it, that point is equidistant, equal distance from all of the vertices of the triangle. So this point here is equal distance from point A, B, and C. It's the same distance. So if you take a triangle, any triangle, and you consider each side a segment on its own. In fact, sometimes it helps to kind of ignore the fact that it's even attached to a triangle. Make the perpendicular bisector of that segment. Right? And then look at the next side of the triangle. Make the perpendicular bisector of the segment. So first you would find the midpoint and then put perpendicular through it. And then the third side of the triangle. Again, you have to kind of treat each one separately. You're going to find the midpoint of that side and then put a perpendicular through it. In every case, every single time, all of those perpendicular bisectors are going to come together at one point, and that's the point of concurrency, since they all three meet together at one point. But what this theorem says is not only do they do that, but that point marks the exact equal distance from each side, each vertex of the triangle. So if you have point here, here, and here, those 3 points Well, if I were going to stand at the point of concurrency and walk to this point, or walk to this point, or walk to this point, it would be exactly the same distance. And there's really only one point that satisfies that, and it's going to be where all the perpendicular bisectors come together. Okay, so that lends itself to these types of problems. A town planner wants to locate a new fire station equidistant from the elementary, middle, and high schools. Where should he locate the station? So you've got the elementary school at point E, the high school at point H, and the middle school at point M. If you create a triangle out of those 3 points, and then you construct or you draw the perpendicular bisector of each side, you're going to get the one point that is equal distance from each of the schools. So that is where the fire station should be placed. Okay, well that point of concurrency where the 3 perpendicular bisectors meet, that point of concurrency is called the circumcenter. The circumcenter is the point where the perpendicular bisectors of a triangle come together. Circumcenter. Circum means around. Center. Okay? So, the circle that we can draw with the circumcenter as its center is going to pass through all the vertices of the triangle, these 3 points. So there's 2 ways of thinking about this. If you have a triangle and you create a circle that passes through all of the 3 vertices of the triangle, you have to have the circle go through those points. Then that is called the circumscribed circle. And it just means that circumscribed means it goes around the circle so that the tips of the shape are touching the circle. I could circumscribe a circle around, you know, a hexagon too, or a this looks like a pentagon here. Circumscribed so that the tips, the points, the vertices are touching the circle. That's what circumscribed around means. Well, it happens to be that the center of that circle that is circumscribed around the triangle, the center of that circle is also the circumcenter of the triangle, meaning it is the point where the 3 perpendicular bisectors are going to intersect. So that point is really loaded with information. It's where the perpendicular bisectors intersect. It's equal distance from the 3 vertices, and it's also the center of the circumscribed circle. So that's going to be true about a circumcenter. Center of circumscribed circle. Oh boy, what does that say? Circle. Center of the circumscribed circle. Equidistant from the 3 vertices. And it's where the 3 perpendicular bisectors intersect. Now this is all describing the circumcenter. Of a triangle. It's the center of the circumscribed circle, it's equidistant from the 3 vertices, and it's where the 3 perpendicular bisectors intersect. Okay. So what about the angle bisectors of a triangle? Well, same idea. If you take a triangle and you construct the angle bisectors, the segments or lines that go through the middle of the angles, dividing the angles into congruent pieces. Those three angle bisectors are also going to intersect at one point. And that point is the point of concurrency of the angle bisectors. Now, this one is not equidistant from the vertices, but it's equidistant from the sides. If you are at this point of concurrency where the three angle bisectors meet, if you were told to walk the shortest distance to each of the edges of this triangle, you would walk along that perpendicular path. Remember, we learned about the distance from a point to a line is along the perpendicular. It's the shortest distance. Well, with angle bisectors, that point of concurrency is equal distance, not to the vertices, to the points this time, but this time it's equal distance to the sides of the triangle. Equally distant to the sides. That point of concurrency is called the incenter. So the incenter is where the angle bisectors of a triangle meet. And now if we're talking about an inscribed circle, if you take any triangle, you could fit a circle inside the triangle so that it just skims the edges of all three sides of the triangle. That's called an inscribed circle. An inscribed circle is just touching all three sides of the triangle. So this time it's inside. Instead of the circumscribed circle went around the outside of the triangle, the inscribed circle goes on the inside of the triangle. And it happens to be that where the angle bisectors intersect, the point of concurrency there, the incenter, is the center of the inscribed circle. This sentence really does make sense. The in-center, these words, make sense. In-center is the center of the inscribed circle. The circumcenter, right? Circumcenter is the center of the circumscribed circle, which we said on the other page anyway. But think about the words. In-center is the center of the inscribed circle. Circumcenter is the center of the circumscribed circle. Okay, so we could be given problems where we solve for x, knowing that in this diagram we have the angle bisectors drawn. If Qn is 5x plus 36 and Qm is 2x plus 51, what is Qo? Well, we can solve for x because since we know this is where the angle bisectors intersect, then we know that these distances are the same. So 5x plus 36 equals 2x plus 51. And then you would solve this, and you would get 3x equals 15 or x equals 5. If x equals 5, we would plug back into these equations. 2 times 5 is 10, plus 51 is 61. So QO would also be 61 since they're equidistant, based on our theorem here of the angle bisectors. Okay, so that is generally going to be the idea here. Just as a recap, we have a point of concurrency is where three lines intersect, And specifically in this lesson, we learned about perpendicular bisectors, and they all come together and meet at one point called the circumcenter. And angle bisectors of a triangle all come together and meet at one point called the incenter. Now the circumcenter is a point that gives you an equal distance to the three vertices of the triangle, and the incenter is a point that marks the equal distance to each side of the triangle. Okay, that's it. I would like you to try this matching and through number 20 here on your own, and we will talk about those answers tomorrow. Thank you.